Salagu Prakalya, a machine learning engineering intern at ASAP Bangalore. And in today's discourse, we will dwell into the realm of LLMs. Our focus will be on Google's cutting edge LLM, the Gemma, augmented with the additional capabilities drawn from the retrieval augmented generation framework. And also, we will leverage a robust ecosystem of tools such as the Hugging Face Transformer Library, Langchain, and the FireSpectre DB by Facebook to build a RAG bot with Varsity's knowledge. And Varsity is a knowledge source provided by Zerodha related to stock, profiles, and marketing. Alright, let's delve into the next one. And these will be the following table of contents throughout this presentation, beginning with basics of RAG and walkthrough of Gemma and its capabilities, a demo of the board that we are going to build with the Varsity's knowledge, and the discussion on the same. What are the future scopes of those board that we probably can implement, and so on. Yeah. So, in today's technological landscape, LLMs they drive numerous natural language applications, right? It's capable of understanding and also generating human-like texts. While they are incredibly powerful, these models can sometimes fall short, and at times they can be overly confident in generating incorrect responses that one might be easily persuaded by their extremely cognate documents. I'm pretty sure that everybody have around come across at least one meme regarding how pretty confident they are with the wrong, incorrect answers, right? And today's LLM they confront two major limitations. Firstly, their knowledge is like bounded by the data available during the training process. So that is a very major drawback of LLMs in general. Secondly, there is this propensity for LLMs to fabricate information, a phenomena often referred to as the hallucination problem when confronted with nuanced or very specific queries. And that's where RAG comes into picture. But why do we need RAG? Well, the answer is simple. LLM cannot solve the problems that RAG can actually address. And what are those? Well, starting with the famous model hallucination problem. The text generation in LLM is based on probability. So, without sufficient factual support, it might generate content that appears serious but lack coherence. Moving on to the data security problem. Generic LLMs they do not have access to the enterprise internal data or say a user private data. So in order to ensure the data security while using the LLM, a good solution is to store these data locally and perform all the data computations locally. And this is like the base foundation of what federated ML is as well, right? So the cloud LLM only serves the purpose of summarizing informations, we could say. And the data and then the data will also be say not leaked and have that could give us a very strong security on our knowledge preserving with our internal boundaries as correct. Next, moving to the answer constraint problem. So RAG provides a more control over the LLM generation. For instance, when a question involves multiple knowledge points, the clues retrieved through RAG can be used to limit the boundaries of this LLM generation. So having clear idea why we deal with RAG, let's move on further on what actually RAG is. So retrieval augmented generation was introduced as a technique to improve the LLMs by incorporating information from external and reliable knowledge bases. So the principle behind RAG was of course straightforward. When asked LLM in question, it does not just rely on what it already knows. Instead, it will first look upon the relevant information from a specified knowledge source. So that way we can look on for factual inaccuracies or accuracies, and we could also be sure that it's not hallucinating or fabricating its answers, right? So RAG and primarily functions through these two phases of process, which is so naive from the name itself. One is the retrieval phase and the second is the generation phase. Moving on. Yeah. So The term retrieval augmented generation, right, the RAG, it actually comes from the paper called the Retrieval Augmented Generation for Knowledge Intensive NLP Tasks from the year 2020 by the researchers from Facebook, University College London, and New York University. So, this is the proposed architecture given in the paper. So what we do here is we start with a knowledge base such as a bunch of texts, say documents ZI here, Z1, 2, 3. These are like bunch of document indexed from Wikipedia, which then is transformed into dense vector presentation called the DSA, and these are called the embeddings, and they use a particular encoder model in order to create this embeddings. Similarly, say if we have a given question X. So here we have 3 example of what a user question can be, and we'll also use the same encoder we used here to create the embeddings over here, and then we transform this into an embedding vector called Q of X. Then we have to find the similarity between DC and this Q of X, right, using a similarity matrix, and generally we use the cosine similarity. Next, we'll encode the questions by the users, and find similar documents in the knowledge base, and these steps are done in this component called the retriever component. So given our question and the additional contexts from the retrieved documents, we can feed this into an LLM called the generator component to get our answer. So this generator component is usually an encoder decoder or a decoder only model. Moving on. So as you could see, we users give the query also called X. So here, while in the retrieving phase, before that we usually do a pre-processing to our vector DB called the indexing. So the indexing processing is like a very crucial initial step that is actually performed offline. So it begins with you say like the cleaning and extracting the raw data, converting into various formats of interest like PDF or a HTML, or say a standard plain text as well. And to accommodate the context constraints of a language model, these texts are divided into smaller and more manageable chunks, and this is a process of chunking. Finally, an index is also created to store these text chunks in the vector DB. So these will be a key value pair which can be more efficient and provide more scalable search capabilities in them. So this is the first phase, indexing phase. Next we have the retrieval phase. So what we do here is the user query is used to retrieve relevant context from external knowledge sources. So to accomplish this, the user query is processed by an encoding model, as we have seen in the proposed architecture, which generates semantically related embeddings again. Then a similarity search is conducted on a vector DB, and that will retrieve top k closest data object, and usually we go with the cosine similarity. And then finally we have the generate or the generation phase, where the user query and the retrieved additional context are filled into a prompt template. And finally this augmented prompt from the retrieval step is given as the input to the LLM. And that's how we get our final retrieval augmented results from the built phase. So there are few major characteristics that I want to pinpoint over here. One is the scalability. RAG reduces the model size and the training costs, and also facilitates a very rapid knowledge expansion as well. And then the accuracy. So since it's based upon the facts and the context that we give, there is a very minimalized occurrence of elisions, giving it a higher accuracy as well. And also coming to the component of explainability, relevant information retrieved served as a reference for the model's prediction, right? And then also RAG can be fine-tuned and also customized for various tasks such as QA, summary, dialogue, etc., similar to a LLMs. So we'll move on to the next major component of our project, the Gemma model given by Google. So Gemma is a family of a very lightweight, state-of-the-art open source model built from the same research and technology used to create the Gemini models from the Google. So there is Gemma 2B and 7B, the first models in the family, redefine portability with the SOTA performance at each of the sizes. So they are also available as a base and also instruction tuned model. So remember, the main reason that we picked up Gemma for our Varsity bot is because it's available as an instruction tuned model only. And also it's also known for its breakthrough performance and multi-framework capabilities, like it's both TPU and GPU optimized, and also we have a community driven innovation behind the screen as well. So the smaller models, they are appropriate for experimentation and localized use cases such as research or education testing performance as well. And with regards to performance, the quality is like not can be very good, but as you could see, here is a comparison between the Llama 2 and Gemma, and we could see it's significantly better than the existing one. And customers, they also pay for and directly manage the underlying hardware for this Gemma model if required, and it also have an 8K context window size as well. And yeah, as usual, it also allows us to customize the model by modifying the underlying weights or requiring AI/ML specialist, and it can be implemented programmatically as well. So moving on to our bot, so we'll have this Gemma model and we'll have it quantized to 4-bit, and then we'll build a framework using the Fires vector DB in the Langchain to integrate our Varsity knowledge within the bot and build a RAG framework. And then finally we could either host it on Streamlit and also or in Hugging Face and share it, or and make it public for, like say, and make it public for further experimentation or community aspect, like community feedback, stuff like that. And in this particular demo, I'll show how you could actually upload, like create the Hugging Face model and upload into the Hugging Face space itself. So we have a collab link, and yeah, the main thing is this can be done both in your CPU or GPU based system as well as the Google collab link. So Google provides a GPU T4 and also TPU, but here we'll make use of the T4 GPU, and let me show you how it is done quickly. Okay, so let's go through the collab. Okay, so yeah, so there are few basic libraries, like very generic one that we will install. Okay, so here we start with the .NET and .env, the transformers and the torch libraries. So here few are like there is bits and bytes for quantization purpose, similarly for accelerate, PyPDF in order to like read our Varsity knowledge database, and also tokenize we use the tick token and sentence transformer library, the Fire CPU version, and Langchain, Streamlit for like to host our model in the end. So yeah, so before moving on, in the original RAG paper, they used BART large as its generator LLM model. So here, like nowadays, like there are like many open source LLMs to choose from. For a RAG chatbot, like we need an instruction model that has been like fine-tuned on conversational data that is small enough for our like local machine to be trained on, right? So for that purpose, we have chosen Google's released Gemma 2B model. Okay, so this can be downloaded and accessed from Hugging Face itself. And for like to actually use this Gemma model, we have to agree on Google's terms of use. By verifying through the Hugging Face, we can actually pass our Hugging Face access token over here and to the transformer API. By that way, you could actually use this Gemma model. So here this is a model, Varsity model, that's trained by me, and I have uploaded in the space. So currently I'm using that as my model ID, but feel free, like if you're beginning from the scratch, please do use it used from the Google Gemma 2-bit model. And following that, what we'll have is to reduce the memory, like we use the 4-bit quantization, which can be done in this collab GPU itself. And we load the model, map the quantization config, and just to make sure like which is the device you are using, either it's CPU or GPU. You can make use of this torch function. So we are currently on the CUDA phase, and here we will start to build our inference, right? So here okay, so before that, like we have to build a prompt as a string. Now this prompt is like formatted according to the training purpose as Gemma. For example, say there's a string called how are you. Okay, so this will be formatted with the BOS token and the start of turn token as a user, with the conversation how are you, and the end of turn and the start of turn model as well. So then this tokenized with tokenizer.encode. So like this is the string, right? And then we'll have the tokenizer.encode, which is fed into the LLM with the model.generate. And the LLM's output tokens are then decoded to make them human readable with the tokenizer.decode function. So basically, instead of giving it as a plain string, it will be like it'll be formatted according to however the Gemma model was trained. So we'll have the respective tokens embedded within the string, and then we'll retrieve the response. So that's how the inference or dot generate works. All right. So yeah, so this is like without the context provided. This is the plain context. So I'm asking, this is actually the dark cloud cover is a term that we generally use as visualizing perspective in the stock market. So when I give context as some random context, so we could see our inference is very clear that it says that context does not provide any information about the dark cloud cover, and it cannot retrieve any answer for that. So when I give the context as null, we could see this is like giving us our answers related to some geographical feature, but clearly that is not the need, right? We need the dark cloud cover related to some stock market jargon to be returned for us. Similarly, evening star is again a stock market jargon used, but then you see when there is no context given, the Gemma model, it gives again some astrophysical answers to us. All right. And similarly, when I give word a spinning top, which is actually a very common phenomenon looked upon in the stock market, this is like the Gemma model when given no context. It generally refers spinning tops as to the toy, and we could see like the answers generated by it. So let's see how our RAG when we trained is going to give very different answers compared to these answers. So beginning with the document loading and splitting phase. So we already installed all the PyPDF and tick token from this, and this is where Langchain comes into play. Alright, so we load, so here I have used model 2, which is nothing but Varsity's module 2 PDF, which talks about the technical analysis, including all the dark cloud cover, visualizing charts, and all those phenomena explained over there. So we use that, and we use the token splitter, and we do the chunking. And this, you could see here, this is a sample extracted data of the page 0, and you could see here page 5, some stock market stuff. Then next we will create our embeddings and the vector store. So here we use the sentence transformer from Hugging Face embeddings. And yeah, so the original RAG paper, they used a BERT encoder for its retrieval component, but we can use whatever encoder model we like. So a list of also a pre-trained encoder models can be found at sbert.net, but here we have used the all mini L2V2 encoder model, which is like only 120 MB in size, and it can encode text into a 384 dimensional vector as well. Okay, and then we also, like, apart from expert.net, you could also look at the MTEB leaderboard, which gives a more thorough overview of what the latest encoder model is. And like it can contains over like 50 datasets if I remember, and around 112 languages for embedding tasks alone. And then, yeah, so for the similarity purpose, we will use the dot product, which is nothing but the cosine similarity. And cosine similarity typically ranges from -1 to +1, where -1 means that vectors are facing the opposite direction, meaning that like zero, meaning like they are like oppositely kind of anatomic kind, and 0 means the vectors are like perpendicular, meaning they're not similar at all, and +1 means the vectors, the embedding vectors, they're facing in the same direction, meaning they're like closely similar. So in this example, you could see as you remember, in the document 0 had only this contents in that, and when I find the similarity between the word analysis and that page content, you could see it is 0.3 something, a decent score. But when I give more relevant contents, similar contents over there, you could see the similarity score rising. So we'll use this to retrieve our top k relevant document, and I mean that's what we need, right? And so the reason that we are doing chunking over here is like one PDF can contain hundreds of pages, right? That cannot be like directly fed into a language model. That's why we have to chunk it and then send into and feed into a language model. Moving on, yeah, okay. So like here I have loaded the PDF files, right? But your Langchain also supports HTML files or a JSON file. You could use anything. The also, yeah, just 1 minute. Yeah, so that is it. Like you could give any format of files, that you could give even the markdown readmes or Microsoft Office files, anything that currently Langchain supports. Next, moving on to the FireDB. So FIRES is a vector database library from Meta's like fundamental AI research team for efficient similarity search and clustering of dense vectors. So we will make use of Langchain's community integration, and and then we'll pass on to a docs variable. This is where the Varsity knowledge is present from the text splitter that we have created, and then we will create all this FireDB in the CPU, the RAM itself. All right. Now, okay. So now when we give our question and then we retrieve our docs from the FireDB using the top k, meaning like the top 5 documents are retrieved, and then we'll have this as a context given for this question. So you could see this is the context that we are giving. So it's nothing but the top 5 retrieved content from our DB. Okay. So when we do that and pass that as a context and this as a question, you could see what is the type of inference that we get. Now we have spinning tops are like type of candlestick patterns that shows decision and uncertainty in the market. So we could see like it's something relevant to the stock market. So we could also, I mean, say for an example, where did you get, say for an example, if we ask the model, where did you actually get this answer from? So we have a factual support, so meaning that we know our answers are context bound, right? So this gives more transparent to the explainability of how this LLM with the RAG works. So similarly, let's give another question, that what is a dark cloud? So earlier, if you remember, it was some geographical based answer, but here these are the contexts that it retrieves. You could see now it gives us chalk. It gives us chalk kind of meaning, right? So now this looks like it's the module 2 of Varsity specific bot. So what is the page retrieve for the documents? Same thing. And when you give now the evening star, if you remember, it was like some random astrophysical answers, right? But then now you see it's purely economically stock based upon our knowledge, and these are the pages that it looked for. So as you could see, we could see like how beautiful this rag is there, right? Okay, so and also you could save this model in your Collab notebook. I mean, like in your G drive itself using this dot save pre-trained command from Hugging Face itself. And this is some sample command that I used to test the model. And remember, like while you set up the HF token, please add your HF token over here like this. Only then you'll be able to access it. Okay, so moving on to how can you load this model to Hugging Face. So first of all, you have to do the Hugging Face CLI login, and here you will be asked for a token. So this can be retrieved from your profile and then just give it. And first of all, you have to create a repository in the Hugging Face website itself, and then you could give that namespace or the name marker over here and just give the model and just enter push to hub option, and it will load the model safe tensors, the config related to the model, everything to the hub. Similarly for the tokenizers. So once that is done, I'll quickly show you how it is reflected. So here is a Varsity model trained by me and released over here, and I recently uploaded over here. If you go to the files section, here you could actually find all the files over here. Readme is just a model card that you can define the config just JSON. This model safe tensor is our Varsity model over like Varsity train model over there, and you can specify requirement.txt if needed, or our tokenizer model. Everything is rolled here. And if you go to your model card, yeah, so yeah, if you want, you would set up this interface over here. And like currently Hugging Face is not, since we like loaded a 4-bit quantized model, Hugging Face currently does not support any, say for example evening store Hugging Face, like yeah, so it's not supporting any 4-bit quantized model. It gives throws error either in bits and bytes or in this format. So this is one thing to be looked upon. Yeah, but that's like regarding training a Varsity rag model. All right, so let's get back to the slides. Yeah, okay, sorry. So what can be the future development? One thing is about graph rags. So knowledge base, they can be represented as as a graphical graph manner, where nodes can be presented as a documents and they can be interlinked. So that way it's like more, more context oriented and more precise over that. And instead of LLM, we can use a OLAMA, and also we could improve our LLM serving in that way. And there are like few techniques to improve our rag itself, starting with the windowing. Windowing is like it's an advanced feature where you can augment the document containing node with the content with the preceding and the succeeding node, meaning like you can also adjust the window of what is the context that you want the neighboring nodes to be participating with the current node. And the second, the hybrid search, that this is like this typically refers to combining the search results from the both the sparse and the dense vectors. When I say dense vectors, it represents the data points as a compact vectors for continuous values, offering very rich and nuanced understanding of the data's features. So these vectors, like they are like often results from the deep learning models such as OpenAI, Mistral, or Gemma as well. Whereas the sparse vectors in context are like primarily zeros, and are like produced through specialized model, like you can use DFIDF for the BM25, etc. Like they excel at identifying specific keywords and minor details, differentiating them from like more semantically rich dense vectors, right? So we could like combine these both results and perform a hybrid search as well. And also we could like index the documents. So llama index, they also provide like we could once indexing we could use the llama index, which provides several evaluators to compute various metrics like faithfulness or context relevancy or answer relevancy. In our current experiment we didn't evaluate any of those, right? So we could make leverage one of those to better understand how a model is. Coming to query rewriting, it involves generating various questions similar to a specific query. This process can be used for like disambiguation or error correction or adapting the query to a specific knowledge base that supports the RAG system. So, and also regarding to the demerits or the challenges that we face in this is like it involves the accuracy of the retrieved. One of the like main challenges of RAG in general is it involves the accuracy of retrieved information and data sources like very heterogeneous. So we should also make sure how we can tackle with that in the future as well. So that pretty much wraps up everything. And if you have any questions, please do reach out. And yep, happy to connect through the social media platform. And I hope this presentation was very insightful. Let me know if there is any comments or any improvements that I can make further as well. Thank you. Please try it out, and there is more future potential that can be built with RAG as well. Please do try out and be active in the community, so together we can develop a reasonable and a faithful AI resource in the future. So thank you.